And so then it's Anton Ovchinnikov. I work at Grid Dynamics, and I will talk about the architecture of the systems for data processing, big data processing, that could be excluded from the open source code. So in-stream processing service blueprint. So then for corporate software. So that's for whom the throughput and production efficiency and reliability are of paramount importance. So what is in-stream processing, and what's in it for business? And then I'll talk how to build the system out of open source components. And then we'll talk about how to build in-stream processing with open source, then about scale and reliability considerations, and I'll just give you a business case that became the foundation of this architecture. So 30 minutes is certainly not enough, and that's why I will only just identify the main points, the bullets. So if you want more details, you can so blog griddynamics.com. This will provide more details. Okay, in processing. So that in-stream processing, that's a big, it's a new approach how to build it. And let's see what are the specifics of big data systems and in-stream processing. So let's see it against this complex landscape of big data services: in-stream processing, batch processing, online applications, data lake, technical support, business analytics. Then on top, so there are two components that do the processing. So which is batch processing, so that has been around for many years, and then in-stream processing that we're going to talk about. And so now it's a mature already. It's production mature, and about several years ago, became a corporate. Mature, industrial mature. And so when we talk about the full data set, so you take it and then we process it. But in the in-stream processing, we never have the full data set. We always have only just increments. We deal with small components. So within the framework of the last window, so it could be one event, several hundreds of thousands events. They range in number. But when we talk about processing one event or 10,000 events, but if it's not a full data set, it's still in-stream processing. Why they need such systems? Why they are? So why just batch processing is not sufficient? And so in the batch processing, we have two phases. So accumulation of data, about several hours, so several scores of hours. So for example, 24 hours. So very widely used cycle of accumulation. Then so we have processing cycle, right? So which can last, I think, from several 10 minutes, 15 minutes, or several hours, depending what is the data set amount. And in spite of the fact that there are many business scenarios that they don't mind that there is a certain delay when you get the data until the time, so when we can use this data to make business decisions. Still, there are many business scenarios where we can just reduce this delay, from hours to minutes, and so that's a good example, a very good example. It's for example, it's a fraud detection system. So if we use batch processing, so we respond. So accumulated, we know just what we have, and we can respond. And that is why. So then to respond earlier, so after several minutes. So this is much better, and so that's why if you respond immediately, so data fraud protection system. So this is very valuable, for example, in some security sensitive things, and so like medicine, so where human lives are at stake. Now that you know that the systems are in demand, now just we can look at how just we can build the system, what we can build it from. And so there are just scores of different projects, and the authors say that they have addressed this issue best and better than anyone. I mean, in-stream processing. But when we start to doubt, we realize that some projects compete, and so we need just to prefer one to another. So some are complementary, so to create and we not integrate them, but one way or the other. So we have this need to, out of many projects, we need to select so the one so with fewer components, and as a result is put together and make a functioning solution. And also then we need certainly them iteration and there are different options like that, and for each selection you need to pay, because first we need to select, then within to put this functioning system together, and then maybe our choice was not very good, and then so we will have spent a lot of time to integrate, to play with them, investing money and effort, and then and there is nothing to show for it, and this will be a great deal of disenchantment, that this business task can be resolved with the help of open source system, and then we abandon the system and we lose money, and so we go to another place, and this is where are the crossroads. I'll give you a shortcut. So why the architecture so this person, why do we, what can we take this, why should we trust what I'm going to tell you? Because this great dynamics, so we create corporate systems on the basis of open source code. So we've been in this business, big data business, for 10 years already, and we have accumulated multifaceted experience. Because our clients, they represent different, we have e-commerce, finance, technologies, advertising, commercials, and in our areas we play. We are the leaders in many of these areas. At the same time, so we not only consume so then projects with open source, but we develop new functionality, and so we check the problems, fix the issues. So we are honest players with the open source code. So then there's the idea of blueprint or the standard model system. So then the world of open source is a big kit with lots of lots of components that you can build anything from them. So lots of cubes of different size, and so you can just make a reliable one or a very fragile one. So and you can always, so then we have always a file and certainly and a screwdriver, so hammer, so you can always just fine tune it, and then you can get carried away with this. And so then the idea is just to offer a shortcut, so for specific terms and conditions, and that will be the fastest and the easiest way to make the system robust at low cost and less time effort. So first, so the system that we develop should be deployable in clouds, cloud ready, and then independent on the cloud provider. And then all the components that are used in the architecture should be integrated. So then integration on top of standard interfaces or originally made out of the box solution. And it should have so a proven mission critical use in big corporate enterprise projects. So here we can see the target performance characteristics. So throughput is 100,000 events per second. So then 100,000 events per second, it's not the top obtainable level. One of our projects that we developed on the basis of this architecture processes a million transactions a second. But when you build a system which is higher than this performance, we need to address many additional so tasks that no need just to inscribe them into a standard system. So latency is 1 to 60 seconds. And then raw data and results achieved for 30 days, retention, reliability, so automatic mechanism of identification of faults, and availability is 5 nines on commodity cloud infrastructure, so which has availability of 3 or 4 nines. Then the conceptual architecture is quite straightforward for components, so which is the aggregator, the buffer, so then queuing, etc. And then if there are short spikes, so prevents losses. Now the second is the key component is the framework for in-stream processing. So parallel distributed environment, a lot of so conveyor of data processing pipeline. Then the third and the fourth is storage, data storage. So we have two different layers. So for optimum use and implementation, so two different systems are needed. First scenario is dealing with the model, with the dictionaries. When you work with dictionaries, so such data has very simple structure, but can be very big. So then, so several scores of gigabytes, and so data changes fast, but they are changed and managed by third-party systems. And we work when you read the data. So then they're easy to store. Then another scenario is intermediary results database. So when we transform the data, but only the data that turns into events, we need the context which is based on the messages that preceded the event or after the event. So the context talks about this state transformation, and for this we have operational store. Although it might be very difficult, and the volume could be hundreds of gigabytes and even more. So besides, so we work with this data. The same, so this for reading and for writing, so the same approach, the same intensity, and the results, so the insights that we get, so we need to upload into outside systems. And so I spoke about the roles, so let's talk about the players now. So what technological stacks we have. So I will just identify the names and show you so the places where they are located. So Apache Kafka, then Spark streaming. So then on Redis and Cassandra is used as an operating storage. So via REST API. Or through the message queuing system, or if there are a lot of data, it could be HDFS, distributed file storage systems. Then, as I was saying, in order to, so that if it's good for, so it should be scalable, if it's to be so industrially used, and they need to be reliable, so that all these components should have these two characteristics. They need to be reliable, and the Kafka and Forks, streaming and Cassandra and Esther, so they're independent projects, all of them, and so with the history, development, evolution, and the task to guarantee the scaling, so will result individual. That's why this model architecture does not have an umbrella approach to ensure the reliability of both characteristics. So this diagram shows the deployment diagram, so the minimum cluster with such properties. You see there's another component of the top level, so which is the Zookeeper ensemble. Zookeeper ensemble, because it does not do anything in the processing or storage, has nothing to do with it, but it's a key component to guarantee reliability, robustness. So how it's achieved, I'll talk later. So now this technological stack. Apache Kafka. Apache Kafka is the queue processing system. So LinkedIn developed it, and then it was released for the license for the open source code. So then the most important part, we recommend pre-selection. Why Apache Kafka? And not something else. So the answer is quite straightforward, because so currently Apache Kafka is absolutely undisputable leader among such systems. And so like other systems, Apache Kafka offers some persistence of data, so everything that gets into queue stays in the storage system and gets on the disk immediately. And then, unlike other systems, only Apache Kafka is very fast. So this is the basis for the next, how it's achieved, but I have no time. And then eventually, so we can interpret Apache Kafka as a database with sequential access. And then Kafka is very efficient and processes the events with the big degree of failures. And so we don't have to erase the message, but change the index of the message, or process it again several days, several scores of days. And we don't have just to do the backup and do the copying. So all we have to do is change the current index and put it back in time, and then continue working. So then another problem is scalable solutions. So that's the strength, because increase efficiency, we add a node and then get the pro rata increase of efficiency. Then Kafka it doesn't lose any data. It's very resistant because everything that Kafka gets copies immediately. It's redundant, and if any nodes fall down, we have a copy immediately that can be brought back into work. And so then this failure-proof system, Kafka works with Zookeeper as an outside service. Let's see what kind of services Zookeeper offers to make it reliable. So then the Zookeeper is service to coordinate distributed calculations. So the first service is providing storage, so with the reliable, consistently made storage, guaranteed consistent storage. So it's a distributed system as well, but at the same time it's a key node, so to guarantee the reliability of other distributed systems. So then guaranteed consistent storage system is very heavy. That's why Zookeeper it's not easy to scale up. So then you can add more nodes and you will get more efficiency. So that's the limitation, and we need to remember it about it. The second service that Zookeeper gives is client monitoring. If the client stops, so then there is a fall. The client is not there anymore, or dies. So then they fall over. Then leader election is another thing. And so in many cases, the distributed system go along the following lines. So it has equal functioning, but one module has a leading role. But so if this module dies, then out of the remaining modules, you select the module that will act as a leader. This is quite, and that's what the Zookeeper does. Selects another module that fills in for the one that died, and then the model architecture has some components that they use Zookeeper to increase its reliability. Hadoop, Kafka, and the resource manager, so to increase their failure protection against failures. Then the next component is Spark streaming. And I think that Spark streaming is the key issue. Why Spark streaming? Why not something else? The thing is that Spark streaming was identified against the background of similar projects when they spoke about that they were planning to invest $300 million to develop this instrument. So functional, so code base enhancement, and invest in a community of developers, data scientists, who would be using Spark as the main instrument when they do their jobs. And so then IBM made this announcement, not just in the void, but it was a logical continuation of their effort and securing leadership that Spark had for a while. Because Spark appeared later, like Flink or Storm and engineering solutions, that we used in development of Spark streaming. So the experience of the systems has been borrowed. And then we had this very lively, happy ecosystem, and so it turned out to be very rich. And then as a result, Spark streaming includes not only in-stream processing, but pipelines, but it has a lot of additional instruments. So the Spark system. So like you said, the SQL language, and so then some libraries have been realized, machine learning and everything. Yeah. Что-то треск пошел. And this is very important when we talk about the full life cycle. So from the beginning to the end. So when the models developed, they need to be personalized, and so they can so process millions of events a second. Another strength of Spark streaming, it's integrated with Kafka very well, and it is used. I use the Kafka capabilities to go back to any event in the past, and then it's out of the box integration with Kafka, easy and easy. So if there's a failure, so we can always bring it all back. And so Kafka has 5 components, so which ensures reliability and failure-proof system. So the next component is Cassandra. Cassandra is the operational storage. So it's parallel SQL database, not only SQL. It's massively scalable, highly available, and OSQL. So Cassandra, so the operational store for streaming applications, so should be ready for a quick increase of volumes and complexity of data stored. And that's you need just to get the product that has a high level of maturity and functionality for possibility for growth. So, for example, setting up distributed system when we have so that this database and distributed in different data centers, and so Cassandra has this capability, and this is a central link, and that is why I cannot expect that if you need it, so you can migrate from simple to more complicated solutions without any risks and losses. That's why Cassandra is the best mature solutions in this area. So Cassandra is a set of nodes, equally functional, no leader. It means that the client, so for reading or writing, can work with any of the nodes, and then sustainable, so failure proof, three nodes. So that's how the guaranteed, how the reliability of the system is guaranteed. And then the last one is Redis as a lookup database. So Redis appeared as shared cache memory, and so then good functionality. So replication, so in-memory data replication, persistence, and but it is not lost in read efficiency. So that's the reason why we selected this component. At the same time, unlike Cassandra, Redis works as active standby. And that means that at every moment in time, only one main node operates as so can do the write function. And if it just breaks, so we need just to do the switching. And the so Redis is guaranteed by its own Redis Sentinel agent that guarantees protection against failure. And so that's what the Zookeeper does, similar to what, but within this new architecture. So for the optimal use of the resources and the hardware, Redis Sentinel is placed in the same nodes where the Zookeeper is located. So we've covered all the pieces, and this is the architecture. It's pretty straightforward, maybe a populated slide, but it's deployment program. So then the minimal cluster, so reliability and efficiency. That's what we need. So all functional modules are redundant, and so we have no point where no weak links, and so then scaling, recovering any component cluster mitigates availability issues, etc. But we cannot say that this architecture is 100% reliable. It's because, like in any distributed system, the configuration of failures can have arbitrary complexity. So, for example, so there was this, for example, the palpitation of the connection line, and so you can see different frequencies up and down. But this is a pathology; it's not the standard, and so, but there's no 100% reliability. Cannot exist here, but still the solution is good, and it's highly reliable anyway. Okay, now let's stop talking about theory. Let's move over to practice. So one of the real projects that became the foundation of this model architecture. So we develop it on the basis of our experience. One of our clients, a big media agency, a case study. So I had lots of digital assets, digital media, and they decided just to start this new project where, on real time, you calculate trends of popularity of their materials. So it's just good to juxtapose them. So hoping that the users seeing the popular trends, so they turn to these materials more often to increase the penetration of the audience. And this is good. It's good for advertising. And here's the key point was it's on the real-time calculation. Then in-stream processing was very useful. And so we had a new technological stack here, which you can see on this diagram. Instead of Apache Kafka, we used Kinesis, just because the client wanted it, Kinesis, because they were connected to Amazon, they used other services of Amazon. So the architecture is quite flexible and allows to replace one with the other. And then the independence of the provider of cloud infrastructure that's why there was this change. Spark streaming was processed events, Cassandra done intermediary calculations, and all the results in S3 and then, by way of conclusion, I'd like to remind you that in-streaming is a hot new technology, and so started very recently. It can process mind-boggling volumes of events in real time and discover insights. And say we can build a whole platform, 100% open source components, not to pay any license money. We'll give you a complete blueprint on how to put it together, and it will run on any public cloud. And this is very, very important for every system. As one of the best strengths is it can, as I said, in public cloud and in any cloud, irrespective of the provider. So we couldn't cover all the subjects, all the topics. We spoke about clouds, but how we deploy it in the cloud. It's part of the architecture that we spoke about, and so it's being developed right now in the final stage, and very soon. So again, just to publish it on our site in the technical blog. And please, this architecture we have to have special implementation. And that will be an application that will be available through Apache license, and you can always so then you can deploy it with one push of a button. So it's from a sandbox, and so you can easily take it if you like it. So you replace one with the other. So the logic is easy. So we listen to Twitter, to tweets, so to certain movie, and dividing to negative and positive comments, and then visualize the data. And that's it. So very soon it will be published, and so it will be on the news. Stay tuned for more news from us. This is it. I think that I have not exceeded my time. There's time left. I can answer your questions. Questions? open source projects I participated, and when they show the systems. So what was the volume of work, and so how long did it take you to put all the systems together to make them work together, yes, and compatible with each other? Thank you. So then you proved indirectly of the reliability of this blueprint. Because to save. Certainly, you're not interested in telling you that we have addressed successfully 10 or 15 issues. But is it up and running? Is it up and running? Is it functioning or not? Is it up and running? Yes, it's up and running. It's just a blueprint. But is there anything else behind this blueprint? So are there any functioning things? So I don't want to be specific because the question is very abstract, and so I will not be specific answering it. So then Spark and Cassandra. So we deployed it in half a year.
Half a year, considering that it was ready for further deployment in other data centers. So for.
Я думаю, это хороший срок. А патчи в компонентах потребовались? А патчи в компонентах? Ну, то есть в Redis, в Zookeeper и так далее, чтобы... Носили ли исправления в открытый исходный? Я не готов ответить на вопрос. Я не настолько глубоко был в этой разработке. Да и следующий вопрос.
How do you test those systems? So you have a flow of events. So, for instance, you processed everything or lost 3%. So when you launch some changes and you try to understand if it works properly or it fails. So if it is a flow of events, so you have to. Well, we have some historical data that we know how the system works on them, and we do some preliminary computation. Then you launch the new code, and we compare the calculated result in the actual. So there is no other option. So the other thing is how to automate this process, and other guys, our guys are doing it. More questions? Yeah, hi, Sergey. So the correlation of random time. Have you correlation of? Could you please specify? I have, for instance, two streams of events that are similar, but we need to find the difference, and the latency between the event is unpredictable. So, and we need to compare the couple of events to match them. Yeah, I think first you cannot forecast them, but still they have some admissible results, some deviations and fluctuations. And in this case, you cannot do it. It's just we will have to make those windows that can place those events. Definitely some events will drop out of those moving windows. And then we can either ignore them once it's not in the window. If it is acceptable, we just forget about it. If these losses are acceptable, we can try to increment them, to calculate it, to account for them incrementally. In any case, you get the two flows, two windows, event windows. We accumulate them, and then we compare the batches. So that's the approach on the whole. There's nothing else. We have one more question. Good. We thank you very much. Did you like it? Interesting? I saw that some people were